alternative low carbon intensity feedstocks that are more evidently available. So being that biomass, municipal solid waste, biogas, then the green hydrogen, or in some instances blue hydrogen, which will then be combined with a source of carbon dioxide. So when we talk about upgrading biomass and municipal solid waste, there are several options available. First of all, one can gasify the material to convert it into a mixture of carbon monoxide and hydrogen. Now, alternatively, these feedstocks can also be pyrolyzed, which is a process that happens at less severe operating conditions in the absence of oxygen, which will essentially result in the production of liquid pyrolysis oil as opposed to a gas. And for that, we have a hardware and RTP technology, as you can also see. Then for the case of ethanol, it is typically converted via fermentation routes when utilizing first generation feedstocks. The examples are corn and sugarcane, then via processes like hydrolysis if second generation feeds are utilized. So when you consider technology maturity levels in addition to cash cost of production, the leading technologies which are really being considered for upgrading these type of materials are the methanol to jet and Fischer-Tropsch to jet technologies. This is expected to grow substantially over the coming years. If it is biomass or municipal solid waste type feed, you need gasification to produce syngas, and if it is biogas, then it can be reformed to produce carbon monoxide and hydrogen by typically utilizing the autothermal reformer. Once carbon monoxide and hydrogen are available, then one can either pursue methanol to jet or Fischer-Tropsch to jet routes. Finally, we have the power to liquid routes, which is utilizing carbon dioxide and hydrogen. So here, carbon dioxide will be converted to carbon monoxide via reversible water gas shift step, or a combination of methanation step followed by a reforming step, or that likely to methanol. In a nutshell, we at Honeywell UP are pathway agnostic. Depending on availability of feed and your preference and cash cost of production, we can work with you to select the appropriate pathway for you. Let's now delve into more details of Fischer-Tropsch pathway with Honeywell UP's Fischer-Tropsch unique cracking technology. If you look at the Fischer-Tropsch pathway from a high level, we can break it down into a high-level three-step processes, where in the first step, syngas will be produced. Depending on the type of feedstock, there are multiple available technologies like gasification, reforming, reverse water gas shift, or electrolysis technologies are available to convert feedstocks into syngas. This syngas is then cleaned up and adjusted to an appropriate hydrogen to carbon monoxide ratio and fed to, as you can see, to a Fischer-Tropsch unit, which is essentially a catalytic process to convert the syngas to a synthetic crude. The synthetic crude is then fed to a hydrocracking unit consisting of hydrocracking reactor to convert C19 plus molecules to jet range and hydroisomerize to meet cold flow properties of SAF. The result is SAF with properties akin to those produced by the HEFA process. The SAF derived from the Fischer-Tropsch route is known as FTSPK, which stands for Fischer-Tropsch synthetic paraffinic kerosene. Investors are drawn to Fischer-Tropsch pathway for several reasons. It's an ASTM approved SAF pathway since 2009 with a high technology readiness level and carbon efficiency, enabling substantial renewable fuel yields. Additionally, the potential to integrate carbon capture units to produce carbon negative renewable fuel products enhances its bankability. Before I go to the further details of Fischer-Tropsch process, you must have seen in recent press release in last November, the Johnson Matthey and Honeywell UP have signed a memorandum of understanding for an end-to-end solution for customers considering either a Fischer-Tropsch or methanol-based sustainable fuels pathway, which drives down operating costs and accelerates the deployment of viable sustainable fuel projects. The partnership brings together Johnson Matthey's leading syngas solutions for both Fischer-Tropsch and methanol pathway and Honeywell's market-leading expertise in fuel upgrading technologies. The objective is to offer single point of technical responsibility to provide seamless and faster execution experience with end-to-end solution. We have been working together for multiple projects globally, and that gives us a confidence to provide right and optimum technology solutions to our customers. Just to be clear, the relationship is non-exclusive in nature, means Honeywell and Johnson Matthey are agnostic to the technology solutions to produce SAF via Fischer-Tropsch or methanol pathway. Let's now delve into the chemistry of Fischer-Tropsch process to gain a better understanding. The Fischer-Tropsch process generates a synthetic crude that is notably paraffinic and devoid of contaminants such as sulfur and nitrogen. This crude primarily comprises three major fractions: lightens, Fischer-Tropsch liquids, and Fischer-Tropsch waxes. From a catalytic perspective, the Fischer-Tropsch process predominantly uses a cobalt-based catalyst as opposed to an iron-based one which were utilized in past. This choice favors the production of longer molecular chains as depicted on the right, resulting in a very low volume of gaseous effluent and a relatively low amount of naphtha. Consequently, even without the recycling and reconverting these components into gas, high SAF yields can be achieved via Fischer-Tropsch pathway. Ongoing innovations in both Fischer-Tropsch synthesis and hydrocracking steps are likely to achieving high renewable fuel yields through the Fischer-Tropsch pathway. You might be aware that the synthetic crude coming out of Fischer-Tropsch synthesis process contains broad spectrum of molecular weights and require upgrading. As we have seen on the slide with the block flow diagram of the Fischer-Tropsch routes, once the synthetic crude is produced, it is then sent to the hydrocracker after removal of the light ends. From a hydrocracking complexity standpoint, it is quite straightforward since the hydrocracker operates at low pressure and does not typically require hydrotreatment. It is a single-stage recycle configuration, which Honeywell UP has many commercial references in different applications. To be more specific, we have more than 80 commercial references, and we are utilizing commercially proven hydrocracking and hydroisomerization catalysts within this process, thus making it straightforward and low risk. The question is, why opt for UP's Fischer-Tropsch hydrocracking technology? The Honeywell Fischer-Tropsch unicracking process is capable of providing 3 to 5% more SAF yield at about 20% lower capex. It also reduces byproduct process and waste streams compared to competing Fischer-Tropsch hydroprocessing technologies. These advantages lead to a higher net present value and IRR, contributing to multiple project awards to Honeywell UP. It is also worth mentioning that Honeywell UP can offer this as modular as well to further reduce project execution risk and overall project schedule for the unicracking block ranging somewhere between 6 to 12 months from overall project schedule. Let's talk quickly about Honeywell UP's Fischer-Tropsch upgrading experience. UP has been actively involved in renewable fuels technology since 1980s. We have experience of designing and licensing a Fischer-Tropsch liquid upgrading technology for a 13-barrel per stream day demonstration facility, and that unit ran successfully for 5 years between 2008 to 2013. We have an experience of 1 barrel per stream day demonstration of single-stage recycle upgrading of Fischer-Tropsch liquids and wax to SPK product for Japanese customer in 2020. We have more than 10,000 hours of pilot plant testing. UP remains a dynamic player in the renewable fuel sector. This commitment to innovation and advancement in technology underscores UP's long-standing dedication to the field. As a proof points of our technology favorability, a recent Honeywell press release of DG Fuels, which highlighted the award for the world's largest FT hydrocracker, which is set to produce 13,000 barrel per stream day of SAF with an expected startup in 2028. The client also plans to build additional units in the United States, utilizing Honeywell UP's Fischer-Tropsch upgrading technology, underscoring the trust and confidence in our solutions. Let's talk about typical project development phases. The typical project development phases spans between 3 to 5 years. The slide illustrates these phases, and I would like to delve deeper into the pre-FID phase, which can last anywhere between 18 to 30 months, depending on the specific project. Breaking down the identify 3 key stages. Phase 1 involves developing a Class 5 cost estimate as a part of the FEL1 deliverable. During this stage, customers and project developers seek high-level budgetary estimates to assess the feasibility of their projects. This phase is crucial for preparing funding applications, environmental permits, offtake agreements, and other administrative requirements, requiring close coordination with licensors. Once Phase 1 is complete, we move into FEL2, which provides a more in-depth analysis of the project to achieve a Class 4 cost estimate. This is typically accomplished through a feasibility study. Finally, we arrive at FEL3, or the basic engineering phase, which enables the final investment decision, or FID, and initiates the EPC phase. The outcome of this stage is a Class 3 cost estimate. Following the FID, the project transitions into the EPC phase, eventually leading to startup, commissioning, and operation. Honeywell UP is equipped to support the customers and project developers throughout all these phases. We have successfully collaborated with multiple clients worldwide, offering technical and project execution expertise, modular solutions, and the right partnerships to provide single-point responsibility, thereby enhancing bankability and minimizing project risks. If you have specific projects or questions about the information provided in the slide, I'm available to discuss them offline. Honeywell UP has a unique strength to offer modular technology portfolio. As customers seek swifter, more efficient, and cost-effective project execution, Honeywell UP provides a modular solution to meet these demands. As you can see on the slide, Honeywell UP has worldwide modular experience with more than 1,800 units operating successfully. Modularization is crucial for several reasons, particularly in industrial settings. It offers a safer and more efficient way to add new units to existing or new facilities, especially when space is limited. It minimizes disruptions to operations due to less on-site construction and congestion. Additionally, modularization reduces material waste and loss in the field. In essence, modularization can lead to significant cost savings, improved quality due to a controlled environment, and faster project completion times. Honeywell UP can work with you to provide seamless modular experience for your specific projects. Thank you for listening. Talk to us to help you navigate the right pathway based on your business model and investment strategies. With technologies that convert the broadest range of feedstocks to SAF and expertise to back it up, we are here to help. Thank you. We are now opening up the floor for the Q&A session. Back to you, Mike. Thanks.
Okay, we will now transition to the question and answer portion of our webcast. For our audience, you can